Hi, my name is Henry Niskanen and my presentation is about blockchain data management. Now, the contents of my presentation will be as follows. First, I will be talking about what is blockchain and what is the motivation for using it. Then I will talk a little bit about its background after moving on to talking about blockchain structure. Finally, I'll be talking about new developments in the blockchain sphere, and then I'll summarize the presentation. Now, what is blockchain? Blockchains are a peer-to-peer distributed network of nodes that together maintain an electronic ledger containing transactions. They do all this without needing a trusted third party for validation or fraud detection. Because of the structure of blockchains, they can provide tamper-resistant and efficient transactions while maintaining the anonymity of their users. So what are the benefits of blockchain? The elimination of trusted third parties comes with numerous benefits. As the blockchain is distributed among multiple nodes, there is no single point of failure in terms of system failure or hacking. This makes transactions in the system more secure. Also, in reality, it is difficult to find a third party that you can trust unconditionally, not to somehow abuse their position when managing a centralized service. The removal of third parties also makes the transactions more efficient in terms of cost and speed, as there is no centralized intermediary that has to manage them. Another benefit is that blockchains are immutable, so any data written cannot be reverted by a malicious party. Changing any data in the blockchain would break the chain and be noticed swiftly. Anyone can also verify and track transactions between different blockchain addresses, while the owners of those addresses are kept hidden. With the decline of physical cash, governments and large payment companies will continue to have more and more control over the lives of individuals. This comes with many negative consequences like the loss of privacy. Also, all assets can also be arbitrarily frozen with a flip of a switch. This can be somewhat rectified with the use of blockchain in the form of cryptocurrencies or electronic cash. Although cryptocurrencies are the most obvious and the most popular use of blockchain, there are other applications such as Internet of Things, smart contracts, supply chain management, identity management, and financial services. Now, my interest in blockchains is that I like their decentralized nature, and with open source code, they can be truly emergent structures. They can naturally emerge on the internet without needing any organizations to back them up or anyone who controls them. The barriers of entry are also quite low, and anyone with an internet connection can join and contribute, no matter their place of origin. The fundamental parts of blockchain began to emerge in the 1990s, with papers describing a distributed network of computers reaching consensus, where one or more of them can be unreliable or malicious. Also, an electronic ledger was described, where a linked chain of signed documents could enable checking that the documents remained unchanged. This made use of Merkle trees, or hash trees, which have been around since the late 1970s. In a hash tree like the one in the picture, the leaves are hashes of data blocks, for example, of documents, and the nodes above them are hashes of their children. This allows an efficient data verification. Then in 2008, Satoshi Nakamoto combined these concepts in the paper titled Bitcoin, a peer-to-peer electronic cash system. Soon after, in 2009, Bitcoin was launched as an open source project, and the first block, called the Genesis block, was mined by Satoshi himself. Bitcoin still remains the largest cryptocurrency by market capitalization, although numerous other cryptocurrencies modeled on Bitcoin have been launched. The identity of Satoshi Nakamoto has never been found out. Some say that instead of one person, he's a group of persons, or that he's already dead. His last correspondence was in 2010, so a decade ago. Bitcoin addresses associated with Satoshi are currently worth billions, but they haven't been touched since he disappeared. Blockchains are structured by having a chain or a linked list of blocks shared among peer-to-peer in a peer-to-peer network. Each block contains some information such as coin transactions in the case of cryptocurrencies like Bitcoin. Blocks are identified by a hash value of the information within the block and the hash of the previous block. Thus, any change to the block in the ledger would break the hash chain and lead to validation failures. The way to add blocks to the blockchain requires reaching a consensus among the nodes in the network. Without a consensus, it would be impossible to maintain a single chain, as the blockchain would quickly diverge into multiple different branches. Now, there are broadly two categories of blockchains, public and private. The differences lie primarily in the way permissions are handled. Public blockchains like Bitcoin are the more common of the two and allow anyone to join the blockchain network and are thus permissionless. Most cryptocurrencies belong to this category. Now, private blockchains, on the other hand, use a third party to authorize nodes that are able to publish blocks to the network. Private blockchains are useful for organizations or businesses who need to have direct control over the blockchain. The use of a trusted third party, however, dilutes a lot of the benefits of blockchain. And transactions are the bread and butter of blockchains. Blockchain transactions are based on asymmetric cryptography, which uses private and public keys. In the case of public or permissionless blockchains, a user can generate as many private and public key pairs as they want. Now, certain blockchain implementations, such as cryptocurrencies, also make use of addresses, which serve as an endpoint for a user's transactions, and a public-facing identifier. Now, they are derived from hashing a public key. Private keys are used as a digital signature associated with a public key. As such, they must be kept well hidden, or else anyone can conduct transactions on the address in question. As securing private keys is so important, users often use software to store them, and this software is called a wallet. They are also able to store public keys and addresses. Now, the process of executing a transaction first starts with a user sending the transaction to a node in the blockchain. The transaction is then propagated to all other nodes in the network. The nodes check that the transaction has the correct format and all the participants are authentic through their digital signature. If the transaction is judged to be valid, it is added to the transaction queue, waiting to be added to a block. The publishing node pools recent transactions together into a candidate block. Blocks contain a block header and block data. A block data consists of the previous block's header hash value, a timestamp, a hash of the block's data, and in certain cases a nonce. I'll talk about nonces a bit later, but they are used in the proof of work consensus scheme. The block's data contains a list of transactions or whatever else the blockchain implementation requires. Once consensus is reached, a certain node can add their block to the end of the blockchain and the process begins again. Consensus models. They're used to determine which of the publishing blocks will publish their own candidate block and thus earn an appropriate reward. This reward is in the form of block rewards or a transaction fee and paid in cryptocurrency. Consensus models ensure that forks, as in a divergence in the chain, are less likely and only a single version of the blockchain is maintained. Blockchain consensus models need to be robust, however, as malicious parties can seek to subvert the network to their own needs. One such attack is called a 51% attack, or double spend attack. It entails more than 50% of the consensus power of the network being owned by a single organization or a group, while 51% attackers cannot create new transactions. They can reverse transactions and prevent others from being confirmed. For example, you could pay a vendor with coin for a service and then create another chain secretly where this transaction does not exist. Since you control most of the network, you can keep adding blocks to it until it becomes the longest chain and thus invalidates the original chain. To avoid this problem, blockchains need to stay distributed with power not concentrated among only a few nodes, as this can lead to such an attack. Although there are several consensus algorithms, the main two types are proof of work and proof of stake. Now, proof of work is vastly the most popular and implemented consensus strategy. It was popularized by Satoshi himself and is used in Bitcoin and Ethereum, the two largest cryptocurrency blockchains. Nodes in a proof of work scheme compete with each other to solve a puzzle which entitles them to add a block to the blockchain. This is controlled through a target number and a nonce number. The objective of the nodes is to hash their block header in such a way that the resulting hash is below the target number. This is controlled with the nonce. Changing the nonce number changes the resulting hash, and this is checked against the target. Solving for the nonce is probabilistic in nature, but having greater computational power means that you can check nonces faster. Once a valid nonce is found, the other nodes validate the answer and the block is added to the blockchain, with the new nonce added into the header. Nodes that participate in solving the nonces are called miners. Now you can adjust the difficulty by either decreasing or increasing the target value. This is done periodically depending on the average time taken on blocks. The fact that computational power increases the monetary reward for miners has led to an arms race among proof of work blockchains for more computational resources. Proof of work has been proven to reach consensus, but the energy costs in the way of electricity have become prohibitive. It has been found that Bitcoin and Ethereum together consume more electricity annually than all but 69 countries individually. Now, the other consensus algorithm is called proof of stake. Now, the proof of stake scheme is achieved by a lottery where the chances are increased by having a larger stake. In the case of cryptocurrencies, this stake is usually the currency itself or some other token related to the currency. It functions in a similar way to stock holding or stock issuing companies. Owning a larger share of the stock grants an investor a higher return. the winner of the lottery is granted the reward from the block. Now, the main advantages of proof of stake over proof of work is that the energy requirements of reaching consensus in proof of stake is pretty much nothing compared to proof of work. Now, detractors argue that the ability to append to a blockchain without expense means that proof of stake won't reach consensus, as it will persist forks, because appending to all branches of the blockchain constitutes a weakly dominant strategy. This problem is called nothing at stake. Proof of work does not have this problem because appending to a branch requires solving for a new nonce, which has a cost in electricity. This ensures that it's in the interest of each node to push blocks only to the most dominant branch, so as not to increase costs. Now, the picture illustrates the nothing at stake problem. If there are two branches A and B with 90% and 10% chance of resolving as the legitimate chain, then a publishing node can ensure their expected payout by appending to both branches. This would exacerbate the fork in the chain. A lack of consensus exists if the forks in the blockchain persist, and they are caused by two or more branches having seemingly equal legitimacy. Branches of the chain can gain legitimacy over the others by being sufficiently larger than the others. An argument against this problem is that the value of the blockchain and the subsequent stakes are decreased by a delayed consensus. This is because blockchains obtain their value by being able to act as a medium of exchange. This requires consensus to be reached as rapidly as possible. So it makes sense for economic sense for nodes in a proof of stake scheme to not delay consensus, if only to avoid losing their stake in the long run. It is thus a wise policy for blockchains using proof of stake to only allow participants with a large enough stake to participate in block validation, as if they have something to lose, they won't act maliciously. Now, smart contracts have been around for a long time, but they have gained popularity in recent years along with blockchain. Smart contracts can be implemented into blockchain itself so that they can be fully or partially self-executing and self-enforcing. Once they are created, they cannot be reversed and will run their course. When related to blockchain, smart contracts can be thought of as a stored procedure whose execution and enforcement are managed by the blockchain itself. These smart contracts can involve practically anything that can be scripted on the blockchain. Some blockchains like Ethereum have a Turing-complete scripting language built into the blockchain, allowing any kind of contract imaginable. A simple case could be the facilitation of a bet between two people. Both of them bet some amount of cryptocurrency on the outcome of, for example, a football match. The contract can then be set to execute after the match, and then the platform searches the internet for the relevant source on the match, and the bet is settled. A more complex case could be the creation of a whole organization using smart contracts. These are called distributed autonomous organizations, or DAO. The whole organization is built within the blockchain, and it is managed autonomously. This organization could provide, for example, financial services like loans. These, however, create security issues in the form of bugs. Since changing any code requires having a consensus, it means that bugs cannot always be rapidly patched. This has happened before with hackers stealing millions in cryptocurrency due to bugs in these organizations. Now, two big challenges facing blockchain today is the electricity usage of proof of work and the throughput or scaling of transactions. The energy use issues can be solved fairly effectively with proof of stake, and we are seeing more and more blockchains moving towards proof of stake consensus models. The throughput issue is more complicated to solve. For example, Ethereum can only process around 15 transactions per second. This limitation prevents most cryptocurrency implementations from competing with traditional payment operators like Visa, who can process thousands of transactions in a second. This feeds into a latency issue as well. With the network only able to handle a few transactions a second, this causes congestion, where it can take individual transactions a long time to be committed to the blockchain. Now, one possible solution to the scaling issue is called sharding, and it is traditionally used in databases, and it involves splitting a dataset into multiple parts and storing them in multiple databases. This shares the load and allows handling of more requests. Now, sharding in blockchain would work in a very similar way. Nodes would be assigned to individual shards, which would manage a part of the blockchain. They would only need to verify transactions assigned to the single shard, and not the whole network. This would allow multiple transactions to be processed in parallel, and would in theory improve scalability. Now, applying sharding to blockchain exposes at least three challenges. Firstly, it requires scalable consensus algorithms like proof of stake. Secondly, nodes must be assigned to shards in such a way that malicious actors cannot compromise any one shard. The third is to enable secure transactions, even if the nodes coordinating transactions are malicious. Currently, Ethereum is in the middle of an update to Ethereum 2, which will implement sharding and proof of stake into the platform, which will prove to be interesting to watch. Now, another development is the Bitcoin Lightning Network, which is in the process of being implemented. It promises to exponentially increase the number of transactions Bitcoin can process. Currently, Bitcoin can only handle about 7 transactions per second, which severely limits its potential as a currency. The average transaction times can take 10 minutes or longer, which is unacceptable if Bitcoin wants to be used in day-to-day purchases. Now, the Bitcoin Lightning Network has been proposed to alleviate this transaction burden. It works by adding a second layer on top of blockchain, through which transactions can be committed. The Lightning Network is administered by Lightning nodes, which are similar to normal blockchain nodes, except they can hold funds and act as a financial intermediary. Their responsibility is also to monitor Lightning channels. Lightning channels are created by multiple users, committing a certain amount of funds to a joint multi-signature wallet. Transactions inside these channels are hidden from the blockchain and require only the signatures of all participants. These commitment transactions essentially just change the balance of funds between the users of the channel. Only once the channel is closed do the transactions get recorded to the blockchain. Since the blockchain does not need to be used with channel transactions, these can be processed almost instantaneously. This also means that transaction costs are much lower. The Lightning Network could potentially allow Bitcoin to scale to billions of users while still retaining the decentralized nature of it. Now, other developments is, for example, Facebook's new cryptocurrency Libra, which is it's launching this year. It will be permissioned, so it will be private. It'll be interesting to see how it pans out, but I'm not very hopeful, as the permission nature will probably throw a lot of people off. Also, numerous governments are planning on adopting blockchain technologies of their own. Venezuela has already launched cryptocurrency, but in their case it isn't doing too well. Now, to summarize, in this presentation we discussed blockchain, its benefits, applications, and how it is structured. We discussed consensus algorithms and how they determine which node gets to publish a block. The two consensus algorithms we looked at were proof of work and proof of stake. We also looked at smart contracts and new developments in the blockchain sphere, like sharding and the new Bitcoin Lightning Network. That's the end of the presentation. Thank you, and if you have any questions, you can send me a message.